Hey, hi everyone. So for this video, I'll just give you a brief uh, concept behind the kinematic equations. So how are kinematic equations derived, and what are the relationship between these kinematic equations with regards to the concept of calculus? So if you could remember, uh, we know that the velocity of a particle, the instantaneous velocity, is equal to the change in position over time. Now, we can manipulate this. We can multiply this dt to the other side. So this will be dx dt equal to dx. Okay? And before I actually do something here, we know that dx, and we assume that dx is the final velocity. We know that dx is equal to the initial velocity dxi plus ax times time. No? So from the kinematic equations to, no? Assuming that the acceleration is constant here, so we have dxi plus axt is equal to, multiplied by dt. So we change this up only enough, is equal to dx. Now, how do we evaluate this, or how do we simplify this equation? Actually, this is called a differential equation. We can use the integral function to eliminate the derivatives. So to find the integral of this function, we can find the integral or the definite integral from the initial time to the final time. So the representation of the curve is this, and the integral of a function is the area of this curve. And with this area of the curve, we could determine actually the position of your object. So there is a relative significance, or a relative or a relationship na lang, a relationship between the velocity function and the position function through integration. So if we integrate this function, we have this as constant, no? Constant din po yung initial velocity. And we are only integrating with respect to dt, which is our variable. So we can disregard the following, no? We're only integrating with respect to t. So with regard to integrating with respect to t, so the derivative of dxi can be determined, and also this one. Now, for the limit, no, I forgot to put in the limit. So the limit is from ti, initial time, to the final time, the initial time to the final time, for both. And integrating this, we have dxi. So dt, na integral of dt here is t. Okay, and then plus, so the integral of this, we have, so assuming this is a constant, now we are only integrating for t. So this will be axt squared over 2. Okay, so this is a definite integral, so we are evaluating from ti to tf. And then this is equal to this. So the integral of dx is just x. Evaluated at ti to tf. Now, to simplify this, ayan, we will just substitute the values of ti and tf for the variables of t here. So for the definite integral, we have the higher the function evaluated at the upper limit minus at the lower limit. So this will be dxi times tf plus ax tf squared over 2, and then minus, we have dxi times ti minus we have plus ax ti squared over 2. And then let's do this as well for the other side. So now how do we substitute this? So the variable of integration here is actually x, and the limit is in terms of the time variable. Therefore, there's a trick to this. So this basically means that we substitute the value of time at this function to get the current position. So this will be x of tf minus x of ti. So what does this mean? So this is just the position at the final, and this is the position at the initial. So this will be just xf minus xi. And another assumption here is that we can simplify the final and the initial time by saying that the final time is just, let's say, t, and the initial time, the reference time, is always 0. So therefore, the tf minus ti will be just 0, will be equal to t minus 0, which is equal to t. So we can utilize this one, no? Or just simplify this, okay, to substitute to our function. So this will be dxi t plus a sub x t over 2 squared minus, so this will cancel out to 0, since we know that ti is equal to 0. So we can just omit this, and then equals to xf minus xi. If we manipulate this, guys, with respect to xf, you can see that xf, okay, is equal to, so looking at this, we have this, and we can transpose this xi here. So we have xi plus dxi plus ax t squared over 2. So this is your derivation for the final position. Isn't that interesting? Okay. And then if you actually find the derivative of this, okay, you will get bx, I'll just discuss this later now, but this will be bx f minus is equal to bxi plus, sorry, we forgot the p here, no? bxi plus axt. Now, if you find the derivative after differentiation, this will be your answer, no? If you do this with respect to time. Okay? So, let's derive also the velocity function, no? Something interesting. So, if you would recall again, we have dx, no? The acceleration, the instantaneous acceleration, is equal to the change in instantaneous velocity over time. So if we do this again, across multiplying this, we have ax dt is equal to dtx. And one thing that we said, no, during our assumptions, that the acceleration is constant. So we can just integrate this, no, directly. So we can transpose, we can factor out the constant here later, so that we are only integrating for t and for dx. So what is the limits of integration? So this is the same thing. We have the initial time and the final time, the initial time and the final time. So this will become what? No? So evaluating this integral. So again, it's just a constant. Therefore, we can just factor this out and find the integral of dt. So the integral of dt is just t. And then due to the definite integral, this is evaluated at ti and tf. So this will be equal to the integral of bx or dbx is bx, and then evaluated at the lower and upper limits ti and tf. Okay, so how do we do this? We can substitute just the values of tf and ti. So we have ax, so you can just say this ax tf minus ax ti. And again, we say that pi is equal to 0. We say that tf is equal to t. So this will be just cancelled out into 0. And this will become t. No? So this will be ax t. And then for the right hand side, integrating this, again, no, a technique here, since the variable of integration is velocity here, and the limit is in the portion, the limit is in time. So basically, we're saying that we are evaluating when substituting this time at this velocity. So this will be bx of tf minus bx of ti. So what does that mean? Meaning, what is the velocity at the time of the final position? And same with this, no, the velocity at the time in the initial position. So this will be just bxf minus bxi. So as we can see here, this looks familiar, no? So if we have this, if we solve for this, we have bxf is equal to, so transposing this to the other side, we have bxi, this will become positive, ano, and then plus axt. So as you can see here, we derive the velocity equation in the previous lesson. Okay? So if you find the derivative, again, no, if you find the derivative of this, you will get this, right? So that will be all. Thank you guys, and see you in class.